coming. So this week we're looking at first sliding mode control, and then we're going to describing functions, which is a pretty fun topic. First of all, I guess I'll just go over sliding mode control for a little bit, and then we'll move on to how we calculate the describing functions. Professor Rock showed you one way in class. I'll show you another way, which I personally think is easier, but it could work either way. So let's see. For sliding mode control, what are we trying to do here? So generally, we've been dealing with sort of bang-bang controllers, and when you have a controller that you can change the magnitude of your control, then you can do something like this, which saves you control authority, and it's generally preferable. So you're given a system some nonlinear system that may look like theta double dot plus f of theta. Right, so some general system like this. And the first thing you want to do here is, if you know these dynamics f, then the best way to control the system is just to say, well, if I can sort of approximate it, then why don't I just work out some logic on the controller side that just cancels this out. So to do that, we're going to divide up our u. So goes to u1 plus u2. And we're going to let u1 equal to some estimate of our nonlinear dynamics. So in your homework you have, theta double dot minus theta equals to u. So right here, right? So that's our nonlinear or undesirable dynamics. Okay. So once you do that, you're left with theta double dot plus f of theta and theta dot equals to some estimate of f plus your u2. So if these are approximately the same, then these will cancel each other out approximately, and you're left with theta dot. So you're just left with a 1 over s squared plant, which we know how to control very well. Once we have that, we can say, oh, we want to follow this line down where this is theta dot plus and the theta equals to 0. So I guess, yeah, I'll just do this. So you do your little trick. And then just move stuff over. And this is your negative lambda, right? That's your slope. So therefore, your u2 is just lambda theta dot. So pretty straightforward. And so that's the main part. So this is what we do when we're on the sliding switching line, or the sliding surface. So if we're off the sliding surface, we would want to be moving towards it. That's why we add this other term. So I'm going to just write it down. So we have our first part, and then we're going to add our, so I think in lecture we called it K, I'm going to call it D, delta, and signum of our sliding surface, which is theta dot plus theta. Right. Or, okay. So I'm saying lambda is 1. Okay, so what this is going to do is, if we're off the switching line, it's going to try to push us back onto the switching line. And when you simulate this, essentially this is all you got to do for the homework. Just got to make a controller and then put it into Simulink and simulate it using, try a bunch of these values, see what kind of curves you get. So just to be complete, I'm going to say U equals to U1 plus U2, which, actually, I won't write it down, where U1 is your minus theta from your homework. Right? So, what's this going to look like? So if we start from an initial condition that's like here, right? In your bang-bang control, you're gonna, with this plan, it's gonna sort of follow a trajectory that's gonna go like that, and then it'll reach the switching line, and then it's gonna chatter down, right? Now, with the sliding mode control, if our delta is now 1, right? If it's 1, then we're kind of getting close to the bang-bang control. If it's less, then what we're saying is this slope right here, so first of all, if delta was 0, right? If delta was 0, then if we look at here, our slope that we would be following would just be negative lambda. So if we had nothing to kick us back to the sliding surface, we would kind of follow a trajectory that's sort of parallel to the switching line, and we would get stuck here, or it would take forever to get back to the origin. So we increase delta, and we start getting stuff that's like this, right? And then it goes to the switching line, and then it follows that down. So that's pretty much question 1. What kind of plots should we generate? Theta plot, U plot, the phase trajectory. And your plot diagram. So, plot the sliding mode control over the bang-bang controller, and just sort of compare them. And that's pretty much it for question 1. Straightforward. Any questions?
Yes. So like if we had delta equals 1, that would have been like the bang bang, and so would have been like curved up like this.
So yeah, I mean, plotted in C, it probably wouldn't be exactly like the bang-bang controller, because you got all the other stuff going on.
Okay.
Right? but as you increase delta, it starts going to the sliding switching line faster.
Yeah.
Yes.
So when we have the f of theta, theta dot cancel with u1 basically.
Yeah.
So like we take our geos plant to get the theta double dot minus theta, and then we say theta double dot is there, so minus theta is just the u1 part.
Yeah.
Right? So what if it had been like 3 theta double dot? Like how do you deal with something like that?
So if it had been 3 theta double dot, then you should have been able to make that into work that into a double dot term.
So like pull out the 3 and then do 1/3 for the second term.
So let me see.
Like if you had like 1 over 3s squared minus 1, then you'd have to rewrite it so that.
So if it's like 3 theta double dot minus theta, like just rewrite that. Right.
Okay.
So you just want to get it into a form that's like this.
Okay.
It's essentially. And this is just for a second order system, right?
Right. So we'll always use sliding mode on second order stuff.
For now.
Okay.
All right. Good. Describing functions. Okay, so in your homework you're asked to calculate the describing functions for a deadband and a hysteresis, and I think that was covered pretty clearly in lecture, so I'm not gonna reiterate that. Just kind of how you do it. You're doing essentially a Fourier expansion of your nonlinearity. So something like if you had Fourier expansion, looks something like this. And since we're only taking the fundamental frequency, and which is C1, we can just kind of eliminate all the other terms, the higher harmonics in the expansion, because we're assuming that our linear part, remember, we have a nonlinear part, we have a linear part. We're assuming that the linear part has enough high frequency drop-off to essentially eliminate all the other harmonics, and when we come back into the nonlinear part, we're only left with the fundamental. So that's a key assumption here. So C1 is 1 over the period what we had in lecture, and so the magnitude of the describing function for nonlinearity is going to be 2 times the magnitude of C1 over A, and the angle of that is just the angle of C1. So we can do it this way. I'm just going to offer you an alternative to this, because So the Fourier expansion, you could either expand it in terms of the complex exponential, or you could expand it in terms of the sines and cosines, right? And sometimes I found that if you expand it in terms of the sines and cosines, it's easier to solve these integrals. You also get a little bit of intuition, and I'll explain how that comes about. So, if you want, try both ways and see which one you like. I'm not saying it's going to be easier for all cases. So, another formulation, we could say the Fourier expansion is some DC term plus a cosine term and a sine term. So now when we're doing the analysis like this, we're looking for, so we don't want the DC term, we want the first fundamental, so that's A1 and B1. So we can approximate our function by A1 cos omega t plus B1 sine omega t. And so there's a lot of trig identities involved here, but you could also write this as a magnitude times sine of some omega t plus a base, and so magnitude would be A1 squared plus B1 squared, and the base would be inverse tangent of these guys. Right. So if we do this, then our describing function, remember it could be a function of the amplitude and the frequency. But right now we're only looking at the amplitude. So this becomes, it's the output over the input. We get so remember our input is just a sinusoidal wave, right? And so we could write that as or we could write it like this. So if I let my input be a sine function, and there's sort of a reason why I'm doing this. I mean, it's the same thing, just shifted, right? So I can write my coefficients A1 then we can let tau equal 0.2 and sub it in those expressions. So why am I doing this? Let's do a quick example. So by the way, the solutions to all of these describing functions are found in the Gelb and van der Velde textbook. So they have, as many describing functions as you can ever hope for. If you want to check your answers in the homework, you can always go. They're all listed in Appendix B. And I've posted this on coursework. Have you guys seen it? Okay. So we'll take one from this book, and it's a nonlinearity we haven't seen before. So it's kind of delta. Okay. So we got a deadband in the middle, and we have gains, essentially, when our input is larger than delta. So we can draw a sinusoidal input, and we can draw what the output looks like, and from that we'll work out the integrals and solve for the describing function. So let me do that. Do that here. So I'm going to do it this way. I'm going to have a sine wave, and then here we have plus delta minus delta. So here's the input, and we draw these critical points over here.
Doesn't matter, there's like a minus. Oh, sorry. I was thinking the sign wave starting at the left.
So, okay, fine. We're going to have 0 here, we're going to go from negative pi to pi. So what's our output going to look like? Let's have a look. So here our input is within this range, right? So our output is going to be 0. Right? So here we have no output. And then it's getting negative, so we're down here. And now it's a straight gain with the gain of alpha. So our output is going to be, again, a sinusoid. It's going to look something like this. Where if this is our input and our input is a sine omega t, right? this output is going to be alpha times a sine omega t is delta. So you can convince yourself that this is the right expression. If we extend this line kind of over, we see that right here, when the input equals the delta, right, our output is 0, but it's on this line, right? So here we see that when the input is delta, is negative delta, right? So when a sine omega t is negative delta, we have the output. This is our output, right? Equals to negative delta plus delta is 0 times alpha. And over here we'll have nothing, and over here we'll have a similar deal. Okay, so that's kind of funky. So we haven't really been dealing with these kind of games yet in class. Let's see. This point over here. So this is, I'll call it tau 1. Actually, I will call this tau 1. This part tau 1. And you can see that, you know, this distance, these distances are all the same, right? Here and here and then here and there. So this point over here is just, I got you know, negative pi over here. I got positive pi over here. So here is just negative pi plus tau. So, is there anything else I want to say? Okay. So let's try to calculate these. Here. First of all, A1. So this is our output, so that f of t refers to this thing. I'm just going to write it down. And I'm just going to replace omega t with tau. So this is 0. So before we evaluate this expression, you can notice a few things. First, we note that this output function over here is an odd function, correct? Cosine is an even function, right? And if you know your kind of odd-even function rules, the product of an odd function and an even function is
0.
It's an odd function. So, but you're ahead of me. So you're correct in the sense that the integral from negative anything to positive the same number of an odd function is 0. Okay. So that's very straightforward, just 0. So, you know, if you do the complex exponential, there isn't like these shortcuts, I guess, that are fairly obvious. So B1. So this one's not going to be 0. So product of an odd function with another odd function is an even function. And we can also say something here is that we could say that the integral from negative pi to pi of an even function is just 2 times that same thing from 0 to pi. And if you're, so if we see this, then all of a sudden we don't have to do anything over here. And if you're even more clever, you could see that over here is going to be the same thing as over here. So, I mean, you could do the whole thing, it's fine. But I'm just going to make the simplification that this is also equal to 4 pi from 4 over pi from L1 to pi over 2. So I'm going to write this down. So okay, so you notice over here it's minus because now we're on this curve. Okay. So over here it's plus delta, over here it's minus delta. Of course you could also just evaluate this portion. It doesn't matter. So that looks like a pretty doable form, and if you do it, I'm not going to go through all the steps, but I'm just going to say that you're going to get something that looks like 4. So alpha times something like that. So what are these tau ones exactly? Okay, let's go for that. Let's see. Well, what we could say is, so this is tau one it's an angle, right? So when A so let's do this one. So when A omega or A sine tau 1 equals to, so that's this function, when that equals to delta, right? Then we know the angle is at tau 1. So we can just reverse that, and then we get tau 1 equals to inverse sine of So we can put that in here. For this one, cos tau 1, what is that? Well, so we have, let's see, take away this. So if we have cos of inverse sine of, okay. Now we can just draw a triangle. Let's say this is our angle tau 1. Okay. Right. So we know that sine of tau 1 is delta over A, which is sine is opposite over hypotenuse. So this is delta, this is A, right? This would be square root of A squared minus delta squared. So cos tau 1 is simply A squared, square root of A squared minus delta squared over A. Yeah, you see that? You can also write this as so you got that one. This one, sine 2 tau 1. You could easily break that into sine is 2 times sine tau 1 times cos tau 1. And that just gives you 2 of sine tau 1 is delta over A, cos tau 1 is so the moral of the story is, so once you work all of that out, you get that the describing function is given by this expression. Okay. So with this example, what I was trying to illustrate is just the little tricks like this one that you're going to be using for your homework. Yeah. Do you have any questions on this?
So when he says that the phase of C1 is equal to the phase of n, if we calculate C1 as like some number times cosine of something, the something inside the cosine is the phase?
So, okay.
Like if, for example, I got that C1 was equal to cosine of inverse sine of delta over A, it seems that he meant that then like the phase of that would be the inverse sine of delta over A.
So when you do it with C1, you would get that C1 is generally a complex number, right? And a complex number, you would either represent it with a magnitude times e to the I j j omega something, or you could do like a plus ib, right? And so when that's the case, then you can convert it to e to the j v.
Okay, so if I just had some.
This is your phase. So.
Okay, so then the phase would be 0 if I had something that was just like.
If it's completely real, right, then the phase is 0. And it's fairly obvious to see from this, like you can tell that the phase is 0, right? Because the output is always in phase with the input. That's going to be the same thing with your deadband. For hysteresis, you're going to have a phase shift.
Okay. And with hysteresis, what happens if your input is like inside of the delta window?
Good question, yeah. So if you're in here, right, then if you're zooming by in here, then it's not going to switch at all. So that means I think your just one.
Because I think you mentioned in class that if the input is less than delta,
Yeah.
then the magnitude of n is 0.
Okay.
Which I guess I'm not even sure what happens when the input is less than delta.
So when the input is less than delta, here is so you have delta, negative delta over here. So you're either here or you're here, right? Is that?
I guess. How would you, like, so would it kind of like just jump onto one of those?
Well, it would depend on the history. Okay, so
I couldn't just start at like the origin?
if you start at the origin, nothing would happen. So let's see. What do you think about that?
Yeah.
Actually, it's probably written on the this one right here.
Sure, I'll check that out.
All right. So that's all I have for today. And no more questions, then good luck with the homework.